Welcome, and thank you for being here. Tonight, we'll gently explore a brief history of black holes, mysterious, silent, and endlessly fascinating. Relax, breathe slowly, and let the universe guide you toward rest. In the vast darkness of space, there exist regions so profoundly strange, so fundamentally mysterious, that for centuries they existed only in the realm of mathematical abstraction and scientific speculation. Objects so dense that they warp the very fabric of reality itself. Places where time slows to a crawl, where the laws of physics as we understand them begin to break down, where even light, the fastest thing in the universe, cannot escape. We call them black holes, and the story of how humanity discovered them is one of the most remarkable intellectual journeys in the history of science. This is not simply a tale of telescopes and equations, though both play starring roles. It's a story that spans more than 2 centuries, from the insights of an obscure English priest in the age of powdered wigs and candlelight, through Einstein's revolutionary reimagining of space and time, to gravitational wave detectors so sensitive they can measure distortions smaller than the width of a proton, and radio telescope networks that transform our entire planet into a single cosmic eye. It's a narrative that weaves together tragedy and triumph, skepticism and vindication, the purely theoretical and the spectacularly observable. What makes this journey so compelling is that black holes represent something genuinely alien to human experience. We live our lives in a universe of solid objects, predictable motions, and familiar physics. Black holes are none of these things. They challenge our intuitions at every turn. They force us to confront the limits of what we can know, what we can see, and what we can understand. And yet, against all odds, human ingenuity has not only proven they exist, we've heard them collide, watched them devour matter, and even photographed their shadows against the cosmic background. The history of black holes is fundamentally a history of expanding human vision, not just the literal vision of seeing farther into space, but the intellectual vision of imagining possibilities that seem impossible and then finding ways to prove them real. The forgotten genius, John Michell, and the birth of an impossible idea. Our story begins not in a modern observatory or physics laboratory, but in the rolling countryside of northern England in the late 1800s. The year is 1783, and in the town of Thornhill near Leeds, there lives a man whose name would be almost entirely forgotten by history, despite the fact that he glimpsed a cosmic truth that wouldn't be confirmed for nearly 200 years. John Michell was born on Christmas Day 1724 in the village of Eakring in Nottinghamshire, England. The world he entered was one still reverberating from the intellectual earthquake that Isaac Newton had triggered. Newton had died just 3 years before Michell's birth, but his influence saturated the academic world. His Principia Mathematica, published in 1687, had given humanity a mathematical language to describe the cosmos, transforming physics from a qualitative, philosophical discipline into a quantitative science. Michell was not the kind of figure who naturally draws the spotlight of history. There exists no portrait of him, no detailed physical description beyond a brief contemporary note that he was a little short man of black complexion and fat, This absence of imagery feels somehow appropriate for a man who would first imagine objects that could not be seen. He spent much of his life as a country rector in the parish of Thornhill, tending to his congregants, delivering sermons, performing baptisms and marriages and funerals. To his parishioners he was simply their priest, a man of the cloth going about the unremarkable business of parish ministry. Yet this humble priest possessed one of the most brilliantly imaginative scientific minds of his era. Behind the clerical collar was a polymath of extraordinary range and insight. Michel had arrived at Cambridge University in June of 1742, when he was just 17 years old. Cambridge at that time was still basking in the reflected glory of Newton's tenure there. Newton had been a student at Trinity College, then a fellow, then the Lucasian professor of mathematics, the very chair that Stephen Hawking would hold centuries later. The university's curriculum was steeped in Newtonian physics and mathematics. Young students like Michel absorbed the revolutionary physics of gravitation, the calculus that Newton had invented, the geometric optics that explained how light behaves. Newton had given the world a new framework for understanding gravity, motion, and the behavior of celestial bodies. He'd shown that the same force that makes an apple fall from a tree also keeps the moon in orbit around Earth and the planets circling the sun. This principle of universal gravitation was breathtaking in its Scope 1 set of laws governing earthly projectiles and cosmic motions alike. The universe was revealed to be not a collection of disparate phenomena requiring different explanations, but a unified system operating according to comprehensible mathematical laws. This was the intellectual landscape in which Michel operated, a world where Newton's laws seemed to explain everything. And Michel proved to be a brilliant student of this Newtonian universe. After completing his studies, he stayed at Cambridge as a teacher, instructing students in Hebrew, Greek, mathematics, and geology. His mind ranged across disciplines with an eclecticism that was more common in the 18th century than it would become later. When science began fragmenting into ever narrower specializations. But Michel wasn't content to simply apply Newton's ideas to known problems. His mind ranged across an astonishing variety of scientific fields, and in each one, he made contributions that were decades ahead of their time. In 1755, a massive earthquake struck Lisbon, Portugal, killing tens of thousands of people and destroying much of the city. The disaster sent shockwaves, literal and metaphorical, through Europe. How did earthquakes work? What caused them? Could they be predicted? Most contemporary explanations involved underground caverns filled with explosive vapors or other speculative mechanisms. Michael took a different approach. He proposed that earthquakes were caused by the movement of rocks deep underground, and that they propagated as waves through the solid earth itself. This was a revolutionary insight. He wasn't just guessing. He analyzed reports of the Lisbon earthquake from different locations and calculated the wave's velocity at roughly 1,200 miles per hour. His work essentially founded the field of seismology. For this achievement, he was elected a Fellow of the Royal Society in 1761, Britain's most prestigious scientific organization. But seismology was just one of Michel's interests. He turned his attention to magnetism and figured out how to manufacture artificial magnets, permanent magnets, created through careful procedures rather than relying on naturally occurring magnetic rocks. He provided what was essentially the first accurate statement of the law of magnetic force, showing that it followed an inverse square law similar to gravity. The force between two magnetic poles decreases with the square of the distance between them. Then he applied statistical methods to astronomy for the first time in history. This might sound dry, but it was genuinely revolutionary. Astronomers had catalogued stars and noted their positions, but no one had thought to ask statistical questions about their distribution. Michel studied how stars were distributed across the night sky and asked, are they randomly scattered, or is there a pattern to their distribution? His analysis, published in 1767, showed that many more stars appeared as pairs or groups than would happen with random alignments. The probability of seeing so many apparent doubles and clusters by chance was vanishingly small. Therefore, Michel argued, these weren't just chance alignments of stars at different distances that happened to appear close together in the sky. They were real systems of double or multiple stars, physically bound together by their mutual gravity. This was the first solid evidence for the physical existence of binary star systems and star clusters. He also conceived and designed experimental apparatus for measuring the force of gravity between masses in a laboratory setting, essentially for weighing the Earth. His ingenious design used a torsion balance, a horizontal bar suspended by a thin wire. By measuring how the bar rotated when massive spheres were brought near it, you could measure the incredibly weak gravitational force between objects of laboratory scale. Michel built the apparatus but died before he could complete the experiment. After his death, it was acquired by the wealthy natural philosopher Henry Cavendish, who used it to perform one of the most important experiments in the history of physics, determining the gravitational constant, g, and thereby allowing calculation of Earth's mass for the first time. Yet for all these achievements, it was a paper Michel wrote in November of 1783 that would prove most prescient, though it would take the better part of 2 centuries for anyone to fully appreciate its significance. Michel had been pondering a question that would ultimately lead to his most far-sighted insight. Could you use light from a star to determine its mass? It was an audacious question for 1783. Astronomers could measure the positions of stars and track their motions across the sky. But determining their actual physical properties, their sizes, their masses, their distances, was extraordinarily difficult. At the time, scientists believed that light consisted of tiny particles, corpuscles as they called them. Isaac Newton himself had championed this corpuscular theory of light in his Optics. And Newton's authority carried tremendous weight. If light was made of particles, Michel reasoned, then those particles would have mass. And if they had mass, they would be affected by gravity, just like any other object. Think about this for a moment. Picture a cannon firing a ball straight up into the air. The ball leaves the cannon with tremendous speed, but as it rises, Earth's gravity slows it down. The gravitational pull is constantly working against the ball's upward motion, sapping its energy. Eventually, the ball's upward velocity decreases to 0. It stops, suspended for an instant, and then it falls back down. The stronger the gravity, the more it slows the ball. Fire the same cannon on Jupiter with its much stronger gravitational field, and the ball wouldn't rise nearly as high. Now imagine that same principle applied to particles of light leaving the surface of a star. A more massive star would have stronger gravity at its surface, which would slow the light particles more. If you could measure how much the light had slowed during its journey from the star's surface, you could, in principle, calculate the star's mass. This was Michel's starting hypothesis, and it's worth noting that it was actually wrong in an important way. Light, as Einstein would prove a century and a quarter later, doesn't slow down in a gravitational field. It always travels at exactly the same speed, what we now call the speed of light, roughly 300,000 kilometers per second. Light doesn't change speed, but it does lose energy in a gravitational field, which manifests as a shift toward longer wavelengths, what we now call gravitational redshift. But Michel couldn't have known this. He was working with the best physics of his time, which was Newtonian physics and the corpuscular theory of light. So Michel worked through the mathematics of his idea. But as he did, he encountered something extraordinary, something that would turn his modest proposal into one of the most prescient predictions in the history of science. In Newtonian physics, there's a concept called escape velocity, the minimum speed an object needs to completely break free from a gravitational field. For Earth, this is about 11 kilometers per second. If you throw a rock upward at 10 kilometers per second, it will slow down, stop, and fall back. But if you could throw it at 12 kilometers per second, it would keep going, gradually slowing but never quite stopping, eventually escaping Earth's gravitational grip entirely. Escape velocity depends on two things: the mass of the body you're escaping from and your distance from its center. The more massive the body, the higher the escape velocity. The closer you are to its center, the higher the escape velocity. If Earth were more massive, or if you compressed it to a smaller radius, keeping the same mass, the escape velocity from its surface would increase. Michel calculated what the escape velocity would be for stars of different sizes and masses. He knew the approximate speed of light from Ole Romer's measurements from the previous century Romer at clock light speed by timing eclipses of Jupiter's moons and noting how the timing varied depending on Earth's position in its orbit. The value Irma obtained was in the right ballpark, though not as precise as modern measurements. And here's where Michel made his leap. What if you had a star so massive, so incredibly dense, that its escape velocity exceeded the speed of light itself? His calculations showed that a star with the same average density as our Sun, but 500 times larger in radius, would have an escape velocity greater than light speed. Think about what this means. If light particles left the surface of such a star, gravity would slow them down. But if the escape velocity exceeded light's speed, the light particles would slow to a stop before escaping and then fall back to the star's surface. They would be captured, imprisoned by gravity. The star would be invisible, dark. You could have an object more massive than hundreds of suns sitting in space, and no amount of light from it would ever reach you. No telescope, no matter how powerful, could detect its light, because there would be no light to detect. He didn't stop there. In a flash of genuine brilliance, Michel realized that while you couldn't see such a dark star directly, you might be able to detect it indirectly. If this invisible object was part of a binary system orbiting a normal, visible star, you would observe the luminous star moving in a peculiar pattern, pulled by the gravity of its unseen companion. From the motion of what you could see, you could infer the presence of what you couldn't. On November 27, 1783, Michel's paper was read to the Royal Society of London. Its title was characteristically verbose for the era, "On the means of discovering the distance, magnitude, and sea of the fixed stars, in consequence of the diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be farther necessary for that purpose." Buried in this lengthy treatise was perhaps the first description of what we now call a black hole, and the first suggestion of how we might detect one. Michel had looked into the mathematical future and glimpsed cosmic monsters that wouldn't be confirmed real for nearly 200 years. The paper made little immediate impression. Part of this was timing within about a decade. The wave theory of light would supplant Newton's corpuscular theory, and since Michel's dark stars were based on the idea of light as particles, the whole concept seemed to rest on faulty foundations. But there was another reason for the idea's obscurity. It was simply too far ahead of its time. Without the technological means to detect X-rays, measure gravitational waves, or observe distant galaxies, there was no way to test Michel's prediction. It remained a curious mathematical exercise, nothing more. Interestingly, a few years after Michel's paper, the brilliant French mathematician Pierre-Simon Laplace independently arrived at essentially the same concept in his 1796 book, Exposition du Système du Monde. Laplace wrote that it was possible that the greatest luminous bodies in the universe might be invisible because their gravitational pull would be too strong for light to escape. Like Michel's work, this insight led nowhere at the time. Michel died quietly in 1793 at the age of 68. His concept of dark stars was forgotten, buried in the archives of the Royal Society. His contributions to seismology and stellar statistics were attributed to others. His name faded from scientific memory. It wasn't until the 1970s, nearly 2 centuries later, that his writings were rediscovered, and scholars realized that this obscure country person had anticipated one of the most profound discoveries in astrophysics. The tragedy is that Michel was essentially right, even if his reasoning wasn't quite correct. Light doesn't slow down in a gravitational field. Einstein would later prove that light always travels at the same speed. But Michel's fundamental insight that there could exist objects so gravitationally powerful that not even light could escape them was profoundly, remarkably correct. Einstein's geometric revolution. For more than a century after Michel's death, the concept of dark stars remained dormant. The 19th century brought tremendous advances in physics and astronomy, but nothing that would resurrect interest in objects from which light couldn't escape. That would require a complete reimagining of what gravity actually is. And that reimagining would come from a patent clerk in Bern, Switzerland. Albert Einstein published his special theory of relativity in 1905, revolutionizing our understanding of space, time, and motion. The special theory was revolutionary enough, showing that time and space aren't absolute but depend on the observer's motion, that mass and energy are equivalent, E equals m squared, that nothing can travel faster than light. But special relativity had a significant limitation. It didn't incorporate gravity. It worked perfectly for objects moving in straight lines at constant speeds or for particles in electromagnetic fields. But it had nothing to say about one of the most fundamental forces in nature. For the next 10 years, Einstein struggled with perhaps the most difficult problem of his career: how to reconcile gravity with his new understanding of space-time. This wasn't just a matter of adding gravity as another force to his equations. The whole point of special relativity was that the laws of physics should look the same for all observers moving at constant velocities. But gravity complicated this picture. How could you have a consistent theory that treated all observers equally when gravity was pulling on everything? Einstein tried numerous approaches, filling notebooks with calculations, pursuing promising leads only to find them leading nowhere. He consulted with mathematicians, learning new mathematical techniques he would need for the final theory. The mathematics he needed, tensor calculus, differential geometry, Riemannian geometry, were esoteric even among mathematicians. Very few physicists understood these tools, but Einstein realized they were exactly what he needed to describe the curved space-time that gravity would create. The breakthrough came in November of 1915, though it was the culmination of years of intensive work. What Einstein produced was so radical, so fundamentally different from Newton's theory, that it required a complete reconceptualization of what gravity actually means. Even today, general relativity challenges our intuitions in profound ways. In Newton's universe, which had dominated physics for more than 2 centuries, gravity was a force, an invisible pull that massive objects exerted on each other across empty space. The Earth pulled on the Moon. The Sun pulled on the Earth, and these forces kept the celestial machinery running. It was elegant, and it worked brilliantly for most practical purposes. But Newton himself had been troubled by it. In the Principia, he wrote that he had been unable to discover the mechanism by which gravity operated. How could objects pull on each other across the void? What was actually being transmitted through empty space? Newton famously said, "I frame no hypotheses." He could describe how gravity behaved mathematically, but he couldn't explain what it fundamentally was. Einstein's answer was breathtaking in its audacity. Gravity isn't a force at all. Instead, mass and energy curve the geometry of space-time itself. And what we perceive as gravitational attraction is simply objects following the natural contours of this curved space-time. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. Now roll a marble past the bowling ball. The marble's path will bend as it moves through the curved region. To the marble, it might feel like it's being pulled toward the bowling ball, but really, it's just following the straightest possible path through the curved surface. There's no force pulling it. The geometry itself is curved. This is what gravity is, according to Einstein. The Sun doesn't pull the Earth with some mysterious force. Instead, the Sun's enormous mass, its energy content, warps space-time in its vicinity. Imagine space-time as a flexible, 4-dimensional fabric, 3 dimensions of space, 1 of time. The Sun creates a deep depression in this fabric. The Earth, moving through space, naturally follows the curves of this warped space-time. From our perspective, this looks like orbital motion. We interpret it as the Earth being pulled by the sun's gravity, but it's really just the geometry of space-time itself. The mathematical equations that describe this relationship. Einstein's field equations are stunningly elegant and horrifically complex at the same time. In their simplest form, they can be written as Gemeng plus the Geraisland Deming Nus plus Thixes GC.cent Betsen Nus Pla. Don't worry if that looks like incomprehensible symbols. What matters is what it represents. On the left side is the geometry of space-time, how curved it is. On the right side is the distribution of mass and energy. The equation says these two things are directly related. Tell me how mass and energy are distributed, and I can calculate how space-time curves. Tell me how space-time curves, and I can infer where mass and energy must be. But hiding within this elegant equation is tremendous complexity. Those Greek letters with subscripts represent tensors, mathematical objects, more complicated than simple numbers or even vectors. The equation is actually 10 coupled, non-linear partial differential equations. Solving them even for simple scenarios is extraordinarily difficult. When Einstein presented his theory to the Prussian Academy of Sciences on November 25, 1915, he included an approximate solution to his field equations that explained a phenomenon that had puzzled astronomers for decades: the peculiar precession of Mercury's orbit. Mercury, the innermost planet, orbits the Sun in an ellipse, as Newton's gravity predicted. But the ellipse itself rotates slowly over time, a phenomenon called precession. Most of this precession could be explained by the gravitational tugs of the other planets, but there was a tiny residual effect, about 43 arcseconds per century, that couldn't be accounted for in Newtonian gravity. Astronomers had proposed various explanations. Maybe there was an undiscovered planet even closer to the Sun, tugging on Mercury. Maybe the Sun wasn't perfectly spherical. Maybe Newton's inverse square law needed a small correction. None of these explanations were entirely satisfying. Einstein's equations predicted the observed precession perfectly, with no adjustable parameters, no fudge factors. The answer just dropped out of mathematics. When Einstein calculated the precession and got the right answer, he later said he was so excited his heart was palpitating. It was a spectacular validation of his theory. But solving Einstein's equations exactly for even relatively simple scenarios seemed impossibly difficult. Einstein himself believed that exact solutions might not exist, or if they did, they would be so mathematically complex as to be useless. Even for something as simple as a spherical, non-rotating mass, the gravitational field of an idealized star, finding an exact solution seemed beyond reach. This belief was about to be dramatically overturned, and it would happen in the most unlikely setting imaginable. The trenches of the Eastern Front in World War I. What's particularly interesting about Einstein's attitude toward the implications of his own theory is his deep skepticism about some of its more extreme predictions. Even as he revolutionized physics, Einstein retained a conservative streak when it came to certain possibilities his equations suggested. He famously stated that nature abhors a singularity, expressing his belief that the universe wouldn't permit the formation of points where density becomes infinite and the laws of physics break down. This skepticism would persist for decades. Einstein would later publish papers arguing that the singularities predicted by his theory couldn't form in the real universe, that some unknown mechanism would prevent gravitational collapse from proceeding to such extremes. In this, as history would show, Einstein was wrong. Nature, it turns out, has no such aversion to singularities. But in late 1915, as Einstein was presenting his revolutionary theory to the world, a German physicist serving on the Eastern Front of World War I was reading Einstein's papers with intense interest, and he was about to make a discovery that would change everything: Schwarzschild's impossible achievement. Karl Schwarzschild was already well established in German scientific circles when World War I broke out. Born in 1873 in Frankfurt, he had made significant contributions to astronomy and theoretical physics, studying everything from stellar spectra to comet orbits. He was the director of the Astrophysical Observatory in Potsdam, a prestigious position that reflected his standing in the scientific community. When war came in 1914, Schwarzschild was in his early 40s, well past the typical age for military service. He could have remained safely at his observatory. But patriotic fervor gripped Germany, and Schwarzschild, like many German intellectuals of the time, volunteered for military service. He was assigned to the artillery and sent to the Eastern Front. The conditions on the Russian front were brutal. Soldiers endured freezing temperatures, inadequate supplies, and the constant threat of combat. Yet somehow, amid the chaos of war, Schwarzschild found time to think about physics. In December of 1915, barely a month after Einstein had published his theory of general relativity, Schwarzschild received copies of Einstein's papers. What happened next ranks among the most remarkable achievements in the history of science. While stationed on the Russian front, while artillery shells exploded around him, while dealing with the brutal conditions of trench warfare, Schwarzschild managed to do what Einstein himself had thought impossible. He found an exact solution to Einstein's field equations. Schwarzschild's solution described the geometry of space-time around a spherically symmetric, non-rotating mass. It was mathematically elegant and physically profound. The solution introduced what we now call the Schwarzschild radius, a critical distance from the center of a mass where something extraordinary happens. For any object, the Schwarzschild radius can be calculated using a simple formula. It's proportional to the object's mass. For the Earth, the Schwarzschild radius is about 9 millimeters, roughly the size of a peanut. For the Sun, it's about 3 kilometers. These numbers might seem abstract, but they have a profound physical meaning. If you could somehow compress the Earth down to the size of a peanut, cramming all its mass into a sphere 9 millimeters in radius, the curvature of space-time around it would become so extreme that light itself could not escape from within that radius. You would have created what we now call an event horizon. The same would be true if you compressed the Sun to 3 kilometers radius. Schwarzschild's solution showed that at the Schwarzschild radius, something peculiar happens to the fabric of spacetime. The radial coordinate and the time coordinate essentially switch roles. Inside this radius, moving outward in space becomes as impossible as traveling backward in time. Everything inevitably and inescapably moves inward toward the center, toward what the mathematics described as a singularity, a point of infinite density where the equations themselves break down. On December 22, 1915, Schwarzschild wrote to Einstein, describing his solution. He concluded the letter with a note that still resonates. "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas." Einstein was astonished. He responded with genuine enthusiasm, admitting he had not expected anyone to find an exact solution to his equation so quickly. He arranged for Schwarzschild's paper to be presented to the Prussian Academy, and it was published in January of 1916. Schwarzschild would solve another of Einstein's problems, finding the gravitational field inside a uniform sphere of matter. He sent that paper to Einstein in February. These would be his last scientific contributions. Sometime during his service on the Eastern Front, Schwarzschild contracted pemphigus, a rare and painful autoimmune disease that causes the skin to blister. There was no cure. In March of 1916, gravely ill, he was sent back to Germany. On May 11, 1916, Karl Schwarzschild died at the age of 42. His legacy was secure, though its full implications wouldn't be appreciated for decades. The Schwarzschild solution was initially regarded as a mathematical curiosity, an interesting but not particularly physical result. After all, nothing in nature could actually be compressed to its Schwarzschild radius, could it? Schwarzschild himself apparently regarded the singularity at the center of his solution as a mathematical artifact rather than a physical reality. This view was widely shared. Throughout the 1920s and 30s, most physicists who thought about Schwarzschild's solution at all considered it purely theoretical. The idea that real objects could collapse to such extremes seemed absurd. Even Einstein, whose equations had made the solution possible, rejected the physical reality of what we now call black holes. But mathematics didn't care about human skepticism. The Schwarzschild solution sat there in the scientific literature, waiting for the universe to reveal that it described real objects. The long skeptical decades. For more than 2 decades after Schwarzschild's death, his solution to Einstein's equations remained an interesting mathematical result without clear physical relevance. The prevailing view among physicists was that while math might predict these exotic objects with event horizons and singularities, nature would find some way to avoid actually creating them. This skepticism wasn't entirely unreasonable. Science is built on the idea that our theories should correspond to reality, and reality in the early 20th century seemed to contain nothing like a Schwarzschild black hole. Yes, stars existed, and yes, they were massive, but they were also enormous, far larger than their Schwarzschild radii. The Sun, for instance, has a radius of about 700,000 kilometers, vastly larger than its Schwarzschild radius of 3 kilometers. What would it take to compress a star to such extremes? It seemed impossible. Stars are stabilized by the outward pressure of the hot gas and radiation in their cores, which balances the inward pull of gravity. As long as a star is burning nuclear fuel, this balance holds. And when a star runs out of fuel, well, that was where things got interesting. In 1930, a young Indian physicist named Subramanian Chandrasekhar made a crucial discovery. During a long sea voyage from India to England, he worked through the mathematics of stellar structure and realized that there was a maximum mass for white dwarf stars. the dense remnants left behind when stars like the Sun die. Beyond about 1.4 times the Sun's mass, the electron pressure that holds up a white dwarf would be insufficient to resist gravitational collapse. The star would have to collapse further. But to what? In 1932, James Chadwick discovered the neutron, opening up a new possibility. Perhaps stars more massive than the Chandrasekhar limit would collapse into neutron stars objects so dense that electrons and protons are forced together to form neutrons. The neutron pressure could, theoretically, halt the collapse. Or could it? In 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project along with his student Hartland Snyder, published a paper that would prove prophetic. They asked what would happen to a star too massive even for neutron pressure to support. Their calculations, using general relativity, showed something startling. Such a star would undergo complete gravitational collapse. There would be nothing to stop it. It would collapse past its Schwarzschild radius and form what they called a frozen star. Frozen because, from the perspective of an outside observer, time would appear to slow down and stop at the event horizon. Oppenheimer and Snyder's work was mathematically rigorous and physically sound. It showed that Schwarzschild's solution wasn't just mathematical abstraction, it described something that could actually form in nature. Yet even this didn't convince the skeptics. The paper was published just days before World War II erupted in Europe. Oppenheimer himself would soon be consumed by the Manhattan Project. The broader physics community largely ignored or dismissed the work. Part of the resistance was conceptual. The idea of a star collapsing into a point of infinite density seemed to violate basic intuitions about how the universe should work. Many physicists, including Einstein himself, felt that some mechanism, perhaps quantum mechanical, perhaps something not yet discovered, would intervene to prevent complete collapse. Einstein made his views explicit in a 1939 paper where he argued that stars could not collapse past a certain point. He believed nature would not allow the formation of singularities. Peter Birdman, who had worked as Einstein's assistant, went further, suggesting that if general relativity predicted such absurdities, perhaps the theory itself needed modification in extreme conditions. The skepticism persisted through the 1940s and 50s. Occasionally, a physicist would publish a paper exploring the properties of these hypothetical collapsed objects, but they remained on the fringes of respectable astrophysics. Most astronomers were focused on more concrete problems: understanding stellar evolution, mapping the galaxy, exploring the newly discovered realm of radio astronomy. What finally began to change minds was a combination of theoretical advances and observational discoveries. The theoretical breakthrough came partly from improved understanding of general relativity itself. In the 1960s, physicists began to better understand the geometry of spacetime near a Schwarzschild radius. They realized that many of the apparent paradoxes, like time appearing to freeze at the event horizon, were artifacts of the coordinate system being used, not fundamental features of the physics. Roger Penrose's work was particularly important. In 1965, he proved a powerful theorem showing that under very general conditions, gravitational collapse would inevitably lead to the formation of a singularity. This wasn't based on any special assumptions about symmetry or the nature of matter. It was a fundamental result of general relativity. If you accepted Einstein's theory, and by the 1960s, the evidence for general relativity was overwhelming, then you had to accept that singularities could form. Meanwhile, observations were revealing phenomena that didn't fit comfortable categories. Quasars, quasi-stellar radio sources, were discovered in the early 1960s. These objects were extraordinarily bright and extraordinarily distant, pumping out more energy than entire galaxies, but from regions smaller than our solar system. What could possibly generate such power? The most plausible explanation involved matter falling into a supermassive object. Perhaps a supermassive black hole. Computer simulations also played a role. As computing power increased, physicists could model stellar collapse in detail, including effects that couldn't be calculated by hand. These simulations showed that under realistic conditions, massive stars would indeed collapse to black holes. There was no magical mechanism to prevent it. John Wheeler, a prominent American physicist who had worked on the hydrogen bomb and pioneered nuclear physics, became an important convert. Wheeler had initially been skeptical of black holes. He preferred the term frozen stars and wasn't convinced they could actually form. But detailed computer modeling in the 1960s changed his mind. Wheeler became not just a believer, but an evangelist, working to popularize the concept and explore its implications. Yet even as the theoretical case for black holes strengthened, and even as observational hints accumulated, these objects still lacked a proper name. They were variously called frozen stars, collapsed stars, or Schwarzschild singularities. The terminology was unwieldy and failed to capture the public imagination. That was about to change, thanks to Wheeler and a fateful lecture in late 1967. The name that stuck. By the mid-1960s, the scientific case for gravitationally collapsed objects had solidified significantly. But the terminology remained awkward. Physicists would speak of gravitationally completely collapsed objects, or frozen stars, or refer technically to Schwarzschild singularities. None of these terms had any punch, any memorability. Science sometimes advances not just through better theories, but through better language, and this awkward phenomenon desperately needed a name that would stick. The story of how that name emerged is itself a fascinating glimpse into how scientific terminology evolves. According to the most famous version of events, John Wheeler was giving a lecture in New York City in late 1967, and he kept having to say, "gravitationally completely collapsed object," over and over. It was exhausting. Then, Wheeler later claimed, someone in the audience called out, "How about black hole?" The name clicked instantly. Wheeler adopted it, used it in a more formal lecture in December of 1967, and included it in the written version published in the spring of 1968. It's a good story, and Wheeler told it many times. But like many good stories, it's probably not entirely accurate. For one thing, the term black hole had been floating around in certain physics circles since at least the early 1960s. Science journalist Marsha Bartusiak, who has extensively researched the origin of the term, found evidence that it was used at a 1963 astrophysics conference in Dallas, Texas, the first Texas Symposium on Relativistic Astrophysics. Even more interestingly, the term appeared in print before Wheeler's famous lecture. Anne Ewing, A reporter for Science newsletter used it in a January 18, 1964 article about a meeting of the American Association for the Advancement of Science. Ewing wrote about how an intense gravitational field could cause a star to collapse in on itself, adding, "Such a star then forms a black hole in the universe." Where did Ewing hear the term? She didn't say, and she's no longer alive to ask. But one intriguing possibility involves Robert Dicke, a physicist at Princeton. Dickie's children later recalled that their father would joke about the Black Hole of Calcutta when something went missing in the house. The Black Hole of Calcutta was a notorious dungeon in British colonial India where prisoners were said to have been crammed into a tiny, suffocating space. Dickie may have transferred this dark metaphor to physics, using it to describe a region of space from which nothing could escape. So if the term existed before Wheeler's 1967 lecture, why does Wheeler get credit for popularizing it? The answer lies in Wheeler's unique position and personality. By the late 1960s, Wheeler was one of the most prominent physicists in America. He had worked on the hydrogen bomb, trained numerous graduate students who became leaders in the field, and had a gift for vivid language and memorable phrases. Wheeler had coined wormhole to describe theoretical tunnels through space-time, and quantum foam to describe the turbulent nature of space-time at the smallest scales. When Wheeler started using black hole consistently in lectures and papers, his authority and visibility gave the term legitimacy. He made it respectable, made it scientific. Other physicists followed his lead. Within a few years, black hole had become the standard terminology. Not everyone was happy about this. Some French physicists initially resisted the term, finding it somewhat crude or even obscene. They preferred their own terminology. But the English term was too vivid, too memorable to be displaced. It captured something essential about these objects: their darkness, their inescapability, their mysterious nature. By the early 1970s, black hole had won. The name proved prophetic in another way. Wheeler had a gift for terminology that wasn't just catchy but conceptually illuminating. Black hole emphasized the key feature of these objects, their absolute darkness, the fact that nothing, not even light, can escape them. This was exactly right. Unlike a frozen star, which suggested something static and cold, black holes suggested something active and consuming. It hinted at the object's event horizon, the boundary beyond which escape is impossible without requiring technical understanding. Wheeler himself never claimed to have invented the term, despite what obituaries often said after his death in 2008. He acknowledged that someone suggested it to him, though he couldn't remember who. What mattered was that he recognized its value and used his considerable influence to propagate it. By the early 1970s, black holes had a proper name. What they still needed was definitive observational proof that they actually existed. The theoretical case was strong. The terminology was now settled. But where were the actual black holes? Were they just mathematical constructs, or were they out there in the universe waiting to be discovered? The answer would come from an unexpected direction, from X-rays streaming from a binary star system in the constellation Cygnus. The first black hole, Cygnus X1. In the early 1960s, astronomers realized they were missing something important about the universe. They were studying the cosmos almost exclusively in visible light, the narrow band of electromagnetic radiation that human eyes can detect. But visible light is just a tiny slice of the electromagnetic spectrum. What about X-rays? What about gamma rays? What cosmic phenomena might be invisible to optical telescopes but blazing bright in other wavelengths? The problem was that Earth's atmosphere blocks X-rays and gamma rays, a fortunate fact for life on Earth's surface, but frustrating for astronomers. To detect cosmic X-rays, you needed to get above the atmosphere. In the early 1960s, the only way to do that was with sounding rockets, small rockets that could carry instruments to the edge of space for a few minutes before falling back to Earth. On a spring day in 1964, one such rocket launched from White Sands Missile Range in New Mexico. It was a modest craft by the standards of the space race then, in full swing, no astronauts aboard, no destination beyond Earth's atmosphere. It carried a pair of Geiger counters designed to detect cosmic X-rays. The flight would last only minutes, but those minutes would open an entirely new window on the universe. As the rocket arced above the atmosphere, climbing above the protective blanket of air that shields us from high-energy radiation, the Geiger counters began clicking. They detected a powerful X-ray source in the constellation Cygnus, the swan one of the prominent constellations visible in the summer night sky from the northern hemisphere. The source was designated Cygnus X1, the first X-ray source found in that constellation. That brief detection, those few minutes of data from a sounding rocket, opened up a mystery that would take years to solve. What was Cygnus X1? It was clearly very bright in X-rays, one of the strongest X-ray sources in the sky. But what kind of object could generate such intense high-energy radiation? Stars emit mostly visible light and infrared radiation. Something extraordinary must be happening at Cygnus X1 to produce so many X-rays. Throughout the late 1960s, more observations accumulated. Different rocket flights detected Cygnus X1 again and again. The X-rays were definitely real, not some instrumental artifact. In 1970, NASA launched Uhuru, the first satellite dedicated to X-ray astronomy. Named after the Swahili word for freedom, and launched from Kenya on that nation's Independence Day, Uhuru revolutionized X-ray astronomy. It could observe continuously rather than for just a few minutes per rocket flight, and it could scan the entire sky systematically. Uhuru studied Cygnus X1 intensively. What it found was fascinating. The X-rays weren't constant. They flickered and varied on timescales as short as 1/10 of a second. This was crucial information, and it told astronomers something profound about the size of the emitting region. Here's why the variability timescale matters. Imagine you have a light bulb that's 1 light second across about 300,000 kilometers in diameter. If you turn on that light bulb instantaneously, an observer watching from a distance wouldn't see it brighten all at once. Light from the near side would reach them first, then light from progressively more distant parts. It would take a full second for light from the far side to arrive. The apparent brightening would be spread out over 1 second, not instantaneous. The same principle works in reverse. If a light source changes brightness in 1/10 of a second, it can't be larger than the distance light travels in that time, about 30,000 kilometers. That's tiny on astronomical scales. Earth is about 13,000 kilometers in diameter, so we're talking about something only a few times larger than our planet. Yet this tiny object was producing enough X-rays to be detected from across the galaxy. But the real breakthrough came in 1971, when two separate teams made a crucial discovery. Paul Murdin and Louise Webster, working at the Royal Greenwich Observatory in England, and Charles Thomas Bolton, working independently at the University of Toronto's David Dunlap Observatory in Canada, both studied the optical counterpart of Cygnus X1, the visible star that marked the position of the X-ray source. They used the Isaac Newton telescope at Herstmonceux in England. Ironically, the telescope's location in England proved to be an advantage despite the notoriously unreliable British weather. Because the weather was poor so often, the telescope had more available time for patient, systematic observations of individual objects. A more productive site would have had the telescope booked solid with various projects. The marginal weather meant Murdin and Webster could observe their target repeatedly over weeks and months, exactly what was needed. What they found was a blue supergiant star, catalogued as HDE 226868. This star is visible through modest telescopes at magnitude 9. It's about 16 times too faint to see with the naked eye, but well within reach of amateur instruments. It appears unremarkable invisible light. But when Murdin, Webster, and Bolton studied its spectrum, the way its light was split into different wavelengths, they saw something extraordinary. The spectrum showed absorption lines, dark lines at specific wavelengths, where atoms in the star's atmosphere absorb light. Different elements produce characteristic patterns of absorption lines, allowing astronomers to determine what stars are made of. But the absorption lines in HDE 226868 weren't stationary. They shifted back and forth in wavelength in a regular pattern, with a period of 5.6 days. This is the Doppler effect in action. Just as the pitch of a siren changes as an ambulance moves toward or away from you, higher pitched when approaching, lower when receding, the wavelength of starlight shifts if the star is moving. If a star moves toward us, its absorption lines shift toward shorter wavelengths, blue shift. If it moves away, they shift toward longer wavelengths, red shift. The regular periodic shifts in HDE 226868 spectrum told a clear story. The star was moving in an elliptical orbit, sometimes approaching Earth, sometimes receding. The period was 5.6 days. That's how long it took to complete one orbit. But orbiting what? There was no visible companion. The only thing at that location, besides the blue supergiant, was the X-ray source. The star must be orbiting the X-ray source. From the period of the orbit and the amplitude of the Doppler shifts, which told them how fast the star was moving, they could calculate the mass of the unseen companion using Newton's laws of motion and gravity. These are the same laws that let astronomers calculate the masses of planets from the orbits of their moons, or the masses of binary stars from their mutual orbits. The calculations were straightforward, but the answer was shocking. The unseen companion had to have at least 8 solar masses, and possibly as much as 16 solar masses, depending on the inclination of the orbit. We see the system somewhat edge on, but not perfectly. which introduces some uncertainty. And remember, this mass was packed into a region small enough that its X-ray emission could vary in a tenth of a second, tens of thousands of kilometers at most. What could it be? A normal star with 8 to 16 solar masses would be an enormous bright star, easily visible. But there was nothing visible at that location. Could it be a white dwarf, a stellar remnant, where a sun-like star's core is compressed to about the size of Earth? No white dwarfs can't be more massive than about 1.4 solar masses. That's the Chandrasekhar limit, discovered by Subrahmanian Chandrasekhar in the 1930s. Beyond that mass, the electron pressure that holds up a white dwarf is insufficient to resist gravity. Could it be a neutron star, an even more extreme remnant where the entire star is compressed to the density of an atomic nucleus? That was more plausible, but there's a problem. Neutron stars also have a maximum mass, called the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses. Beyond that, even neutron pressure can't hold the star up against gravity. The object in Cygnus X1 appeared to be far more massive than either limit. It couldn't be a white dwarf. It couldn't be a neutron star. What else could it be except a black hole? This was the smoking gun, or at least it seemed like it should be. But science demands skepticism, and there were reasons to be cautious. The measurement uncertainties were significant. Maybe the mass estimate was wrong. Maybe the orbital inclination was different than assumed. Or maybe there were other stars in the system complicating the dynamics. Maybe there was some exotic form of matter we didn't know about that could support a star beyond the neutron star limit. Maybe the whole interpretation was somehow mistaken. And yet, the evidence was compelling. The more astronomers studied Cygnus X1, the more the black hole interpretation made sense. The rapid X-ray variability suggested a very compact object. The high mass pushed it well beyond the limits for white dwarfs and neutron stars. The X-rays themselves had the characteristics expected from an accretion disk gas spiraling into a compact object, heating up to millions of degrees through friction, and emitting high-energy radiation before crossing the event horizon and disappearing forever. And yet, skepticism persisted. The measurement uncertainties were significant. Maybe the mass estimate was wrong. Maybe there was some exotic form of matter we didn't know about that could support a star beyond the neutron star limit. Maybe the whole interpretation was mistaken. This uncertainty spawned one of the most famous wagers in the history of science. Stephen Hawking, the brilliant Cambridge physicist who had done groundbreaking theoretical work on black holes, made a bet with his Caltech colleague, Kip Thorne. The bet was about whether Cygnus X1 contained a black hole. Thorne, confident in the evidence, bet that it did. Hawking, perhaps surprisingly, bet that it didn't. Why would Hawking, of all people, bet against black holes? The answer is both scientific and personal. Scientifically, Hawking knew that extraordinary claims require extraordinary evidence. The evidence for Cygnus X1 being a black hole was strong but not yet definitive. There were still possible loopholes, still alternative explanations, but there was also a personal reason. As Hawking later explained, he had invested enormous effort in understanding black holes theoretically. If it turned out that black holes didn't actually exist in nature, all that work would be wasted. The bet was insurance if black holes didn't exist, At least he'd win a subscription to Private Eye magazine. The stakes were intentionally trivial. If they did exist, he'd lose the bet, but his research would be vindicated. Throughout the 1970s and 80s, evidence accumulated. Better measurements refined the mass estimate of the unseen companion, pushing it higher, making alternative explanations less plausible. Improved observations of the system revealed more details about how matter was flowing from the visible star toward the compact object. The picture became clearer. Gas from the blue supergiant was being pulled away by the intense gravity of the compact companion. This gas formed a swirling accretion disk around the compact object, and as it spiraled inward, friction heated it to millions of degrees, causing it to emit the X-rays that made Cygnus X1 so bright. In 1990, with the evidence now overwhelming, Hawking conceded the bet. He broke into Thorne's office with help from Thorne's students and left a signed concession. The terms of the bet meant Thorne won a one-year subscription to Penthouse magazine, a characteristically cheeky touch. Cygnus X1 had provided the first convincing evidence for a stellar mass black hole, but the evidence was still indirect. We couldn't see the black hole itself by definition. Black holes are invisible. We could only infer its existence from its gravitational effects on its companion star and the X-rays from the accretion disk. The case was compelling, but it was circumstantial. More direct evidence would require a completely different approach, one that would take decades to develop and would involve some of the most sensitive scientific instruments ever constructed. The evidence would come not from light, but from ripples in the fabric of space-time itself. Gravitational waves, hearing the unhearable. While astronomers were gathering evidence for black holes through X-ray observations and orbital mechanics, another group of physicists was pursuing a different kind of detection, one that went back to Einstein's original equations. When Einstein formulated general relativity, he realized that his equations predicted something remarkable. Just as accelerating electric charges produce electromagnetic waves, radio waves, light, X-rays accelerating masses should produce gravitational waves. These wouldn't be waves in some medium, like sound waves in air or water waves in the ocean. They would be ripples in the geometry of space-time itself. Einstein himself was skeptical that these waves could ever be detected. He calculated that they would be extraordinarily weak. Even violent cosmic events would produce gravitational waves that, by the time they reached Earth, would be almost infinitesimally small. In one of his papers, he wrote that the prospects for detection were so poor as to be essentially hopeless. But Einstein underestimated human ingenuity. In the 1960s, Joseph Weber at the University of Maryland began experimenting with aluminum cylinders designed to vibrate slightly if a gravitational wave passed through them. These Weber bars were the first serious attempt at gravitational wave detection. Weber claimed to have detected signals, but other scientists couldn't replicate his results, and the physics community concluded that Weber bars simply weren't sensitive enough. The next generation of detectors would be completely different. Instead of solid bars, they would use light. The basic concept is called laser interferometry. You send a laser beam to a beam splitter, which divides it into two perpendicular beams. These beams travel down long arms at right angles to each other, bounce off mirrors, and return. When they recombine, they create an interference pattern, bright and dark fringes determined by the precise distance each beam traveled. Now, if a gravitational wave passes through the detector, it will stretch space in one direction and compress it in the perpendicular direction. This means one arm gets slightly longer while the other gets slightly shorter. The change is minuscule, far smaller than the width of an atom, but it's enough to shift the interference pattern. By measuring this shift, you can detect the gravitational wave. The idea was conceptually simple but technologically nightmarish. To detect gravitational waves from realistic astrophysical sources, you needed to measure changes in length smaller than 1/10,000th the diameter of a proton. You had to isolate your detector from every possible source of noise, seismic vibrations, passing trucks, ocean waves, even the quantum jitter of the atoms in your mirrors. The technical challenges seemed almost insurmountable, but in the 1980s and 90s, driven primarily by the vision of physicists Rainer Weiss at MIT and Kip Thorne and Ronald Drever at Caltech, the project that would become LIGO, the Laser Interferometer Gravitational Wave Observatory, began to take shape. The National Science Foundation agreed to fund construction of 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana. They were deliberately placed thousands of kilometers apart so that a signal seen in both detectors, with the time delay matching the speed of light travel time between them, could be distinguished from local noise. Each detector consisted of 2 4-kilometer-long arms arranged in an L shape. Inside these arms, laser light bounced back and forth hundreds of times between mirrors, effectively extending the path length and making the interferometer more sensitive. The entire system was evacuated to prevent air molecules from scattering the light. The mirrors were suspended by elaborate isolation systems designed to dampen all vibrations except those caused by gravitational waves. Initial LIGO began operations in 2002 and ran for nearly a decade without detecting anything definitive. The instruments were working, but they weren't quite sensitive enough. What was needed was an upgraded advanced LIGO with improved lasers, better mirrors, more sophisticated isolation systems. The upgrade took years and cost hundreds of millions of dollars. Advanced LIGO began its first observing run on September 14, 2015. The detectors had been active for just hours. They were still in what's called the engineering run phase, checking that all systems were working properly before the official science run began. It was 5:51 in the morning in Louisiana, 4:51 in Washington state. Most of the LIGO team were asleep or just starting their day. At that moment, traveling at the speed of light, a ripple in space-time passed through Earth. It had been traveling for 1.3 billion years, gradually weakening as it spread outward from its source like ripples on a cosmic pond. By the time it reached Earth, it was almost inconceivably faint. But advanced LIGO was just barely sensitive enough to detect it. At Hanford, Washington, the gravitational wave passed through the detector. For a fraction of a second, it stretched one of the 4-kilometer arms slightly while compressing the other, then reversed, compressing the first while stretching the second. The changes were tiny, smaller than 1/1000th the diameter of a proton, but the laser interferometer detected them, and the pattern was recorded digitally. 7 milliseconds later, the time it takes light to travel from Louisiana to Washington, the same wave passed through the Livingston detector, which registered an almost identical signal. The signal was remarkably clean. It started at a frequency of 35 Hz lower than the lowest notes on a piano, and swept upward to 250 Hz over about 0.2 of a second. The amplitude increased as the frequency rose, creating a characteristic rising chirp, then abruptly cut off. The waveform matched theoretical predictions so perfectly it almost seemed too good to be true. The LIGO data analysis pipeline, running automatically, flagged the signal within minutes. Automated alerts went out to collaboration members. Scientists began logging in remotely, pulling up the data, staring at the waveforms in disbelief and growing excitement. Could this be real? Or was it some kind of test? A simulated signal injected into the data stream to test the analysis procedures. The collaboration had a protocol for such blind injections, fake signals that only a few people knew about, designed to test whether the team could properly identify and analyze a real gravitational wave if one occurred. But as more people checked, as more analysis was done, it became clear this wasn't an injection. No one had been authorized to insert a signal. The detection was real. To physicists who had been studying general relativity for decades, the pattern was unmistakable. It was exactly what you'd expect from two black holes spiraling toward each other and merging, a process called a binary black hole coalescence. The rising frequency corresponded to the two black holes orbiting faster and faster as they drew closer together. The increasing amplitude reflected the intensifying gravitational field as the masses converged. The abrupt cutoff marked the moment of merger, when the two black holes combined into a single, more massive black hole. But identifying the signal was just the beginning. Now came the painstaking work of verification and analysis. Every possible alternative explanation had to be examined and ruled out. Was it a glitch in the electronics? A coincidence of noise at both detectors? Some environmental disturbance? A passing truck? An earthquake? Atmospheric pressure changes? The detectors had thousands of auxiliary sensors designed to monitor every conceivable source of noise. All of them had to be checked. The collaboration set up a series of working groups to examine different aspects of the data. One group analyzed whether the signal could be explained by instrumental artifacts. Another compared the observed waveform to theoretical predictions. A third examined the statistical significance. How likely was it that random noise could produce such a signal? The analysis took months. The detection had occurred in September, but the collaboration didn't announce it until February of 2016. This caution was deliberate. Extraordinary claims require extraordinary evidence, and they wanted to be absolutely certain before making a public announcement. As the analysis progressed, the details of what had happened 1.3 billion years ago became clear. The waveform could be matched to theoretical templates, computer simulations of how gravitational waves from merging black holes should look. By comparing the observed signal to these templates, physicists could decode the story of the collision. The analysis showed that 1.3 billion years ago, in a galaxy far away, two black holes had been orbiting each other. One had about 36 times the mass of the Sun. The other had about 29 solar masses. These weren't stellar mass black holes formed from the collapse of individual massive stars. They were intermediate in mass, larger than typical stellar remnants. For perhaps millions or even billions of years, these two black holes had been locked in a gravitational dance, orbiting their common center of mass. As they orbited, they emitted gravitational waves, ripples in space-time that carried away energy. This energy loss caused the orbit to gradually shrink. The black holes spiraled slowly closer together. In the final minutes before the merger, the process accelerated dramatically. The black holes were now orbiting so close together and so fast that they were emitting intense gravitational radiation. In the final seconds, they were whipping around each other at significant fractions of the speed of light. 30%, 40%, faster and faster. The gravitational field became increasingly intense, the space-time curvature increasingly extreme. Then, in a cataclysmic moment lasting less than a quarter of a second, they merged. The collision was so violent, so energetic, that 3 solar masses worth of material, an amount of mass equivalent to 3 times the entire mass of our Sun, was converted into pure gravitational wave energy. Think about that for a moment. 3 suns worth of mass converted to energy in a fraction of a second. Einstein's equation, Ex², tells us how much energy that represents. The speed of light is a very large number, 300,000 kilometers per second. When you square it and multiply by mass, even a tiny amount of mass converts to an enormous amount of energy. 3 solar masses is 2 times 10 n 100 kilograms. Converting that much mass to energy releases about 1.8 times 10 n 100 kilos. For comparison, our Sun's total energy output, all the light and heat it radiates in every direction, is about 4 times 10 squared 4 times 1, or joules per second. The black hole merger released its energy in about a quarter of a second. For that brief instant, the gravitational wave power output of this collision exceeded the combined light output of every star in the visible universe by a factor of 10. Think about that. More power than all the light from all the stars and all the galaxies we can see, radiated in gravitational waves from a region of space less than 200 kilometers across. Those gravitational waves radiated outward at the speed of light, spreading through the universe in an expanding sphere. As they traveled, they gradually weakened, their amplitude decreasing with distance. By the time they reached Earth, having traveled 1.3 billion light-years, they were incredibly faint. They stretched and squeezed space by less than 1,000th the diameter of a proton. But advanced LIGO, with its 4-kilometer arms, its ultra-stable mirrors, and its exquisitely sensitive laser interferometry, was just barely sensitive enough to detect them. The detection, designated GW15200914, for gravitational wave, and the date was announced on February 11, 2016, in press conferences around the world. The announcement was accompanied by papers in Physical Review letters presenting the data and analysis. The scientific community was electrified. This wasn't just the first detection of gravitational waves, though. That alone would have been momentous enough. It was also the first direct confirmation of binary black hole systems and the first observation of a black hole merger. The implications rippled through multiple fields. For general relativity, it was a spectacular confirmation. Einstein's century-old equations predicted the waveform with exquisite precision. For astrophysics, it revealed that binary black holes could form and merge within the current age of the universe. For astronomy, It opened an entirely new window on the cosmos. Gravitational wave astronomy was born. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish for their contributions to LIGO and the detection of gravitational waves. Thorne's bet with Hawking had been vindicated in the most dramatic way possible. Since that first detection, LIGO and its Italian counterpart Virgo have detected dozens of gravitational wave events. Some are binary black hole mergers like GW152914. Others are mergers of neutron stars, which produce both gravitational waves and electromagnetic radiation, allowing for coordinated observations across multiple wavelengths. Each detection adds to our understanding of these mysterious objects and the violent processes that create them. But gravitational waves, for all their importance, still don't give us a picture of a black hole. They tell us about black hole collisions, about masses and spins, about the ripples these events create in space-time. But we still hadn't seen a black hole itself. That final frontier would require yet another technological marvel: an Earth-sized telescope, the Event Horizon Telescope, photographing the unphotographable. To understand why photographing a black hole is so challenging, you need to appreciate the scales involved. Black holes are, paradoxically, both enormous and tiny. A stellar mass black hole might have a mass 10 times that of the Sun, but an event horizon only 60 kilometers across. A supermassive black hole might have a mass billions of times the Sun. But even then, its event horizon is measured in billions of kilometers large on human scales, but tiny compared to the distances to other galaxies. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A, pronounced Sagittarius A star, has a mass about 4 million times that of the Sun. Its event horizon is roughly 24 million kilometers in diameter, big enough to swallow Mercury's orbit. But Sagittarius A is 26,000 light-years away from Earth. Its event horizon appears about 50 micro-arcseconds across. That's roughly equivalent to seeing a donut on the moon. To resolve such a tiny object, you'd need a telescope the size of Earth. Obviously, you can't build a single telescope that large, but you can simulate one through a technique called Very Long Baseline Interferometry, or VLBI. The basic idea is to use multiple radio telescopes spread across large distances and combine their signals. The resolution you achieve depends not on the size of individual telescopes, but on the maximum separation between them. Link telescopes on opposite sides of Earth, and you effectively have an Earth-sized telescope. This concept had been around for decades, but applying it to black holes required solving extraordinary technical challenges. You needed telescopes that could observe at millimeter wavelengths, short enough to see through the hot gas around black holes and resolve their shadows. You needed to synchronize the observations with atomic hot precision across telescopes on different continents. You needed to process absolutely staggering amounts of data so much that it had to be physically shipped on hard drives rather than transmitted over the internet. The Event Horizon Telescope project brought together 8 radio observatories scattered around the planet. They included ALMA in Chile, the South Pole Telescope in Antarctica, the IRAM 30-meter telescope in Spain, and 5 others strategically positioned to maximize coverage. Each side had to be equipped with specialized recording equipment and atomic clocks, hydrogen masers, that keep time with such precision that they lose only 1 second every 100 million years. The observations had to be carefully planned and coordinated. All telescopes needed to point at the same target at the same time, and weather had to cooperate at all sites simultaneously, a challenging requirement when your observatories are scattered from Hawaii to Spain to the South Pole. The project initially targeted 2 supermassive black holes. Sagittarius A was an obvious choice. It's the closest supermassive black hole to Earth. But it presented a challenge because it's relatively small. As supermassive black holes go, the hot gas around it evolves rapidly, changing significantly over the course of a single observation. Trying to image Sagittarius A was like trying to photograph a toddler who won't sit still. The second target was the supermassive black hole at the center of the galaxy Messier 87, or M87. This galaxy, in the constellation Virgo, is much farther away, about 55 million light-years. But its central black hole is a monster with a mass of 6.5 billion solar masses. From our perspective, despite being much farther away, M87's black hole appears about the same angular size as Sagittarius A because it's so much larger. And crucially, because it's so massive, the gas around it evolves much more slowly, making it an easier target to image. In April of 2017, over the course of several days, the 8 telescopes of the Event Horizon Telescope turned their focus on M87. Each telescope recorded data continuously, generating hundreds of terabytes of information each day. The data was so voluminous that it couldn't be transmitted electronically. It had to be stored on specialized hard drives and physically flown to processing centers at MIT and the Max Planck Institute in Germany. Then began the painstaking work of turning that data into an image. This wasn't like processing photographs from an ordinary camera. The raw data consisted of complex electromagnetic wave patterns recorded at different locations at different times. Sophisticated algorithms had to combine this information, accounting for Earth's rotation, atmospheric effects, instrumental characteristics, and more. Multiple independent teams worked on the data using different imaging techniques to ensure the results were reliable. The process took 2 years. On April 10, 2019, in simultaneous press conferences around the globe, the Event Horizon Telescope collaboration revealed their results. They presented an image, the first ever photograph of a black hole. The image showed a bright orange-red ring surrounding a dark central region. To understand what you're looking at, you need to know that this isn't like a normal photograph. Black holes are, by definition, black. They don't emit light. What we're seeing is light from the superheated gas around the black hole. Gas from nearby stars or the interstellar medium falls toward the black hole, but it doesn't usually fall straight in. Instead, conservation of angular momentum causes the gas to settle into an accretion disk, a swirling disk of material orbiting the black hole. As the gas spirals inward, friction between adjacent layers heats it up. The temperatures become enormous, millions of degrees. At these temperatures, the gas glows brilliantly across the electromagnetic spectrum. The ring in the image is light from this accretion disk. But it's not a simple image of the disk. The black hole's intense gravity bends the paths of light rays in complex ways. Light that would normally travel in straight lines gets curved, creating multiple images and distortions. Some light from the backside of the disk gets bent around the black hole, allowing us to see it. The result is that we see a circular ring of light from the disk, even though we're viewing the system from a particular angle. The dark central region isn't the black hole itself. It's slightly larger than the event horizon. It's what's called the black hole's shadow. This is the region of space from which light is so strongly bent or captured by the black hole's gravity that it cannot reach us. Even if there were a powerful light source at that location, we wouldn't see it. The shadow is about 2.5 times larger than the event horizon. That factor of 2.5 comes from the way light bends in the black hole's gravitational field. The ring isn't uniformly bright. It's significantly brighter on one side than the other, creating a crescent-like appearance. This asymmetry isn't random. It's due to a relativistic effect called Doppler beaming, or relativistic beaming. The gas in the accretion disk is orbiting the black hole at a significant fraction of the speed of light, perhaps 30% of light speed or more. The gas on one side of the disk is moving toward us, while the gas on the opposite side is moving away. When a source of light moves toward you at high speed, its light gets compressed and amplified. It appears brighter and bluer. When it moves away, the light gets stretched and dimmed. It appears fainter and redder. This is the Doppler effect in the relativistic regime. The result is that the side of the accretion disk rotating toward us appears much brighter than the side rotating away, creating the observed asymmetry. The image perfectly matches what general relativity predicts for a rapidly spinning black hole viewed from our particular angle. Theoretical physicists have been creating computer simulations of what black holes should look like for years, and the Event Horizon Telescope image matched those simulations remarkably well. This wasn't just a picture. It was a powerful test of general relativity in the most extreme gravitational conditions we can observe. The image also allowed astronomers to refine their measurement of the black hole's properties. By carefully analyzing the size of the shadow and the distribution of light in the image, they confirmed the mass of M87's black hole at 6.5 billion solar masses, with an uncertainty of about 10%. That's an almost incomprehensible mass 6 billion. 500 million times the mass of our Sun, all concentrated in a region you could fit inside our solar system. The event horizon itself has a diameter of about 40 billion kilometers. That sounds enormous, and by human standards it is. You could fit multiple solar systems inside it. But M87 is 55 million light-years away. A light-year is about 9.5 trillion kilometers. 55 million light-years is roughly 5.2 times 10 squared. Philly. And squared our distance. Even a 40 billion kilometer object appears incredibly tiny, about 40 micro arcseconds across. That's equivalent to seeing a donut on the moon, or reading a newspaper in New York from Paris, or resolving a tennis ball on the moon. The technical achievement of the Event Horizon Telescope cannot be overstated. To create an Earth-sized telescope, 8 observatories had to work in perfect synchronization. They used atomic clocks, hydrogen masers, accurate to better than 1 part in 10 imager. That's like keeping time so accurately that you wouldn't be off by even 1 second over tens of millions of years. The observations had to be coordinated across time zones and hemispheres. Weather had to cooperate at all sites simultaneously, a challenging requirement when your observatories are scattered from Hawaii to Spain to Antarctica. If clouds or technical problems knocked out even one telescope, it would reduce the quality of the final image. Each telescope recorded data at an extraordinary rate, about 64 gigabits per second. Over the course of a night's observations, each site would generate hundreds of terabytes of data. The total data volume from all 8 telescopes over the entire observing campaign was about 5 petabytes, roughly equivalent to all the photos on Facebook at the time, or the entire Library of Congress digitized about 70 times over. This data couldn't be transmitted over the internet. There's simply too much of it. Instead, it was stored on specialized hard drives filled with helium, which allows the drives to spin with less friction and pack more data. These drives were then physically shipped to central processing facilities at MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany. The drives from the South Pole Telescope had to wait until the Antarctic winter ended and flights could resume before they could be shipped. At these processing facilities, supercomputers combined the data from all 8 telescopes. This wasn't like stitching together pieces of a photograph. The raw data consisted of complex electromagnetic wave patterns recorded at different locations at different times. Sophisticated algorithms had to cross-correlate this data, accounting for Earth's rotation, atmospheric effects at each site, the precise positions and orientations of each telescope, instrumental characteristics, and more. Multiple independent teams worked on creating images from the data using different algorithms and approaches. This redundancy was crucial for verification. If different teams using different methods all produced similar images, it increased confidence that the image was real and not some artifact of the analysis procedure. The public reaction was overwhelming. The image appeared on front pages around the world. It became the most downloaded image in the history of the National Science Foundation's website. It spawned countless memes and artistic interpretations. For many people, it represented something profound, visible proof of objects that until recently seemed like mathematical abstractions. The Event Horizon Telescope didn't stop with M87. In May of 2022, they released the results of their imaging of Sagittarius A, the supermassive black hole at the center of our own galaxy. This was a more challenging target because of how quickly the gas around it changes, but the team developed sophisticated techniques to account for this variability. The resulting image shows a similar ring structure, confirming that the object at the heart of the Milky Way is indeed a supermassive black hole. These images represent an extraordinary achievement. The first direct visual evidence of black holes. The first photographs of objects whose existence was predicted more than a century ago and seemed impossible to observe. They demonstrate the power of international scientific collaboration, the triumph of human ingenuity over seemingly insurmountable technical challenges, and the continuing ability of Einstein's equations to describe the universe with remarkable precision. Black holes today, understanding the incomprehensible. We now know that black holes aren't rare cosmic oddities but common features of the universe. They come in different varieties, formed through different processes, playing different roles in cosmic evolution. Stellar mass black holes form when massive stars, those at least 8 to 10 times more massive than the Sun, reach the end of their lives. When such a star exhausts its nuclear fuel, it can no longer generate the heat and pressure needed to resist gravitational collapse. The outer layers explode in a supernova while the core collapses. If the core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, even neutron pressure cannot halt the collapse. The core collapses past its event horizon, forming a black hole. We've now detected dozens of stellar mass black holes through various methods. Some, like Cygnus X1, are in binary systems where we can observe their gravitational effects on companion stars. Others have been detected through gravitational waves from merging binary black holes. The masses we've measured range from about 5 solar masses up to around 100 solar masses. Then there are supermassive black holes, monsters with masses from millions to billions of times the Sun's mass. These lurk at the centers of most, possibly all, large galaxies. Our own Milky Way harbors Sagittarius A, with its 4 million solar masses. The black hole at the center of M87 has 6.5 billion solar masses. Some of the most massive known black holes exceed 20 billion solar masses. How supermassive black holes form is still an active area of research. They're too massive to have formed from single star collapse. Probably they grew through a combination of processes, smaller black holes merging together, and black holes accreting enormous amounts of matter over billions of years. Some may have formed from the direct collapse of massive gas clouds in the early universe. We're still working out the details. There's also likely a third category, intermediate mass black holes, with masses from hundreds to hundreds of thousands of solar masses. These would bridge the gap between stellar mass and supermassive black holes. We have some candidate observations, but intermediate mass black holes remain the most mysterious category, with their existence and formation mechanisms still debated. Black holes aren't just passive objects sitting in space. They're active participants in cosmic evolution. The supermassive black holes at galaxy centers appear to play crucial roles in regulating star formation. When matter falls into these black holes, it releases enormous amounts of energy. More than nuclear fusion, this energy can heat and blow away gas that would otherwise form stars, effectively shutting down star formation in the galaxy's central region. There's a remarkable correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, suggesting a deep connection between black hole growth and galaxy evolution. Some black holes are extraordinarily active, accreting matter at prodigious rates and producing jets of particles that stream outward at nearly light speed. These jets can extend for millions of light years, far beyond the galaxy itself. The energy carried by these jets can affect the intergalactic medium, influencing the formation and evolution of galaxy clusters. Yet for all we've learned, fundamental mysteries remain. Perhaps the deepest is the information paradox. Quantum mechanics says that information cannot be destroyed. If you know the exact quantum state of a system at one time, you can, in principle, calculate its state at any other time. But when matter falls into a black hole, all its detailed quantum information seems to be lost forever, erased from the universe. This appears to violate quantum mechanics. Stephen Hawking added a twist to this puzzle in 1974 when he showed that black holes aren't completely black. Through a quantum mechanical process now called Hawking radiation, black holes should emit a faint thermal glow and slowly evaporate. A stellar mass black hole would take longer than the current age of the universe to evaporate. But in principle, even black holes eventually die. When they do, what happens to the information about everything that fell in? This information paradox has driven theoretical physics for decades. Some physicists think information is somehow encoded in the Hawking radiation. Others suggest it might be stored in subtle correlations at the event horizon. Some radical proposals involve multiple universes or modifications to quantum mechanics or general relativity. We still don't have a definitive answer, and resolving this puzzle may require a full theory of quantum gravity, something we don't yet possess. Another frontier involves testing general relativity in the strongest gravitational fields we can access. So far, Einstein's equations pass every test we can devise, even in the extreme environments near black holes. The gravitational wave signals from merging black holes match general relativity's predictions to exquisite precision. The shadow of M87 has exactly the circular shape Einstein's equations predict, but we keep looking for cracks, for hints of where general relativity might break down, because we know it can't be the complete story. It doesn't incorporate quantum mechanics. We're also learning about the environments around black holes. The accretion disks of gas spiraling into black holes are laboratories for extreme physics matter, moving at significant fractions of light speed, magnetic fields of incredible strength, temperatures of billions of degrees. We're using observations from X-ray telescopes, radio telescopes, and gravitational wave detectors to map these regions in increasing detail. New instruments are coming online that will expand our capabilities further. The James Webb Space Telescope is studying the early universe, potentially revealing supermassive black holes from when the universe was young, helping us understand how these monsters grew so large so quickly. Next-generation gravitational wave detectors are being planned that will be even more sensitive than LIGO, able to detect mergers from across the observable universe. Upgrades to the Event Horizon Telescope will allow for better resolution and, potentially, movies showing how the gas around black holes evolves over time. The cultural echo: black holes in our collective imagination. Black holes have escaped the confines of academic journals and entered popular culture in ways few other scientific concepts have. They've become metaphors, plot devices, sources of wonder and terror, symbols of the unknown and unknowable. Part of this cultural resonance comes from the inherent drama of what black holes represent. They're cosmic monsters, regions where the normal rules break down, gates to possible other universes, the ultimate destroyers. They tap into deep human fascinations with boundaries, with the forbidden, with what lies beyond the edge of the known. Science fiction embraced black holes early. From the 1970s onward, they appeared in countless novels, movies, and television shows. Sometimes the portrayal was scientifically dubious, black holes as cosmic vacuum cleaners, sucking up everything around them, or as magical portals to other dimensions. But increasingly, filmmakers and writers have worked to get the science right, or at least plausible. The 2014 film Interstellar represents perhaps the most scientifically accurate portrayal of a black hole in mainstream cinema. The filmmakers worked closely with Kip Thorne, using actual general relativity calculations to simulate what a rapidly spinning black hole would look like. The resulting images of the black hole Gargantua showed the light from the accretion disk being bent and distorted in complex ways, creating a visual representation that was both scientifically accurate and aesthetically striking. Yet even scientifically informed portrayals involve creative choices. Interstellar shows Gargantua with a bright, visually appealing accretion disk. In reality, depending on viewing angle and accretion rate, a black hole might appear much dimmer, or its surroundings might be obscured by gas and dust. The movie had to balance scientific accuracy with visual appeal and storytelling needs. Black holes have also served as metaphors in broader cultural discourse. Jean Baudrillard wrote about black holes as symbols of modernity's tendency to absorb and nullify meaning. The term black hole gets applied metaphorically to anything from financial problems to organizational dysfunction. Any situation where resources seem to disappear without a trace. The actual photographs of black holes from the Event Horizon Telescope generated extraordinary public interest, partly because they made these abstract objects concrete and visual. The images were simultaneously familiar. They looked similar to artistic renderings we'd seen before, and profoundly strange. They confirmed that reality can be as bizarre as fiction. The discourse around black holes has also intersected with broader conversations about science communication, diversity, and representation. The Event Horizon Telescope collaboration included researchers from around the world, and the project highlighted the importance of international cooperation. The prominent role of Katie Booman, whose algorithm work contributed to generating the images, sparked important conversations about women in science and the often invisible contributions of early career researchers to major discoveries. There's something poetic about black holes capturing the public imagination so thoroughly. These are objects we cannot directly see, that exist at distances we cannot comprehend, governed by physics that defies everyday intuition. Yet through mathematics, ingenuity, and collaboration, we've made them real. We've measured them, photographed them, heard them collide. We've turned the invisible visible, the abstract concrete. Looking forward, the continuing mystery. As we stand in 2026, we've come an astonishing distance from Jean-Michel's speculation about dark stars in 1783. We've transformed black holes from mathematical curiosities to observed phenomena. We've detected them through X-rays, through gravitational waves, through their effects on stars and gas. We've photographed their shadows. We've measured their masses and spins. We've watched them collide and merge. Yet in many ways, we're still at the beginning of black hole science rather than the end. Every answer we've found has generated new questions. We're planning next-generation gravitational wave detectors that will be orders of magnitude more sensitive than current instruments. The Einstein telescope, proposed for construction in Europe, would be a 10-kilometer scale underground observatory capable of detecting black hole mergers from the edge of the observable universe. The Cosmic Explorer, proposed for the United States, would have 40-kilometer arms, allowing it to detect the earliest black hole mergers from when the universe was young. These instruments won't just detect more events, they'll see different kinds of events. They might detect intermediate mass black holes merging, filling in a crucial gap in our understanding. They could observe black holes eating neutron stars, revealing how matter behaves under the most extreme conditions. They might even detect unexpected phenomena we haven't yet imagined. The Event Horizon Telescope is expanding as well. Adding more observing sites will improve resolution and allow for better image quality. We might soon be able to make movies of black hole environments, watching how accretion flows and jets evolve over time. We could test general relativity with even greater precision by measuring how light bends in the most intense gravitational fields. Space-based gravitational wave detectors are in development. LISA, the Laser Interferometer Space Antenna, will consist of 3 spacecraft flying in formation millions of kilometers apart, forming a triangle. From this configuration, in the pristine environment of space, LISA will detect lower frequency gravitational waves than Earth-based detectors can, opening windows on supermassive black hole mergers and other phenomena, invisible to LIGO. We're also getting better at studying the environments around black holes. X-ray observatories can map the innermost regions of accretion disks, where matter is spiraling into black holes at relativistic speeds. We can measure how black holes spin by studying how their rotation drags space-time around them. The frame dragging effect predicted by general relativity. We can watch jets launching from near the event horizon and trace how they evolve over millions of light years. Theoretical work continues on fundamental questions. Physicists are still grappling with the information paradox, with what happens at the singularity hidden inside a black hole, with how to reconcile general relativity and quantum mechanics. Some are exploring whether black holes might be connected to other universes through wormholes. Others are examining whether apparent black holes might actually be different kinds of exotic objects, gravistars, fuzzballs, or other theoretical possibilities. We're also investigating how black holes affected cosmic history. Did primordial black holes form in the very early universe? And if so, do they contribute to dark matter? How did supermassive black holes grow so large so quickly in the early universe? What role did black holes play in reionizing the universe and regulating galaxy formation? Each question leads to more questions. Each observation reveals new mysteries alongside solving old ones. This is the nature of science at the frontier. The more we learn, the more we realize how much we don't know. But what's remarkable is that we're asking these questions about objects that, not long ago, were considered purely theoretical, possibly non-existent. We've gone from speculation to detection to detailed study in less than a century. We've transformed black holes from mathematical abstractions to observed phenomena that we can photograph, whose collisions we can hear, whose properties we can measure. The journey from John Michael's dark stars to the Event Horizon Telescope's photographs spans 243 years. It encompasses some of humanity's greatest intellectual achievements: Einstein's reimagining of gravity, Schwarzschild's wartime calculations, the decades-long quest to detect gravitational waves, the technological marvel of an Earth-sized telescope. It's a story of persistence in the face of skepticism, ingenuity in solving seemingly impossible problems, and the gradual accumulation of evidence turning speculation into established fact. We live in what some astronomers call a golden age of black hole research. The instruments we've built, the observations we're making, and the theoretical framework we're developing are revealing these cosmic mysteries in unprecedented detail. We're not just confirming that black holes exist. We're studying their properties, their environments, their roles in cosmic evolution. Black holes remain strange, exotic, profoundly mysterious. They're places where our physics breaks down, where space-time becomes so warped that our equations start giving infinite answers. They're laboratories for testing general relativity in its most extreme limits. They're cosmic archives that may hold clues about the fundamental nature of information, time, and reality itself. And they're humbling. These objects remind us how bizarre the universe can be, how much stranger reality is than everyday experience suggests. They challenge us to expand our intuitions, to think beyond the familiar, to accept that the cosmos doesn't conform to human expectations. But they're also inspiring. The fact that we've managed to study these objects at all, that we've detected ripples in space-time from black holes colliding billions of years ago, that we've photographed the shadow of a black hole 55 million light-years away, speaks to the power of human curiosity and ingenuity. We're clever apes on a small planet, but we've figured out how to peer into the darkest corners of the universe. The history of black holes is still being written. We're living through some of its most exciting chapters. The observations we're making today, the instruments we're building, the theoretical insights we're developing, these will shape how future generations understand these remarkable objects. From Michel's prescient speculation to Einstein's geometric revolution, from Schwarzschild's wartime breakthrough to Wheeler's gift for naming, from the X-ray astronomers who found Cygnus X1 to the gravitational wave detectors that heard colliding black holes, from the global collaboration that photographed Maurepas, from the global collaboration that photographed M87 to the theoretical physicists still grappling with information paradoxes, this journey represents some of the best of human science. Black holes started as impossible ideas, mathematical curiosities that seemed too strange to be real. Today they're established features of the cosmos, objects we can observe and study. Tomorrow they may help us unlock the deepest mysteries of physics, revealing the quantum nature of gravity, or the ultimate fate of information, or the structure of space-time at its smallest scales. The story of black holes is, ultimately, a story about expanding the boundaries of human knowledge. It's about taking ideas seriously even when they seem impossible, developing the tools to test those ideas, and following the evidence wherever it leads. It's about persistence, creativity, collaboration, and the willingness to be surprised by what the universe reveals. We've come so far. We have so much farther to go. And that's what makes this such an exciting time to be exploring these darkest, densest, most mysterious objects in the cosmos. If you found this journey through the history of black holes fascinating, please hit that like button and subscribe to Behind the Space for more explorations of the cosmos and the human quest to understand